Alright, chemistry students from Borger High School. This is Chemistry Unit 4, Atomic Structure and History. There are three major TEKs that you guys are responsible for. The state of Texas says that you will understand the experimental design and conclusions used in the development of the modern atomic theory, including Dalton, Thomson, Rutherford, and Bohr's experiments. C3F, you'll need to research and describe the history of chemistry and contributions of scientists. And C6D, you're going to have to use isotopic composition to calculate, average atomic mass of an element. Alright, look at the first page of your notes. And if you look, you'll see that we start off with Roman numeral number 1, atomic theory. But before we do that, a lot of people always want to, be persnickety and say, well, you just proved to me that atoms exist. And, it's the atomic theory, but it's got some solid basis for being called a theory. Remember that a theory is generally consists of multiple hypotheses that have seemed to be getting the same data again, same answers again and again and again. So we've got some pretty solid evidence. What you see here in the lovely picture is a little stick man, and it's made out of carbon monoxide molecules. Each of the little bumps on here are going to be is one atom. Now that's a really what you see here, those little bumps, that's pretty much the best picture of an atom that we can have. So we can't see down into the atom and see the protons and neutrons and electrons, but they can't have actually taken pictures of atoms like this. This was taken through a scanning tunneling microscope, something that obviously we don't have here at this school. It's going to be something, a really advanced microscope that we don't have. We start with Roman numeral number 1, atomic theory. And if you go way back before the time of Christ, so that'd be BC, a little bit before BC, then what we have is the Greeks talking about trying to explain what everything was made of. And there were some that decided that, hey, if you take a piece of stuff, you can break it down into smaller and smaller and smaller and smaller pieces until you get to the smallest piece, and it just can't be divided anymore. And one particular Greek guy, Democritus, write that down, called that tiny indivisible little sphere or piece an atom. You'll notice that also on the slide here it says that we're going to see a molecularian video. I can't wait. You'll see that tomorrow in class. Aristotle, you guys all know, all are familiar with Aristotle. Aristotle was also a Greek guy, and he was like the Einstein of the day, and pretty much what he said went. And he didn't go with this whole idea of atoms. His theory of what everything was made of is that everything was made of one of four things: earth, air, fire, or water. And since he was the big dog, he pretty much ran Democritus out of town. He had him banished from the area because that whole atom thing was just radical belief. And as a matter of fact, Aristotle's thinking process and his science was actually followed up into the 1700s. So it really kind of set us back a little bit from that one. All after Aristotle's time, a lot of what we would call chemists of today were actually alchemists, where they used this theory of everything's made of earth, air, fire, and water, and they kind of expanded it, and they said, okay, everything has a little bit of everything else in it. So if it does, then maybe we could get, if there's a rock that you have in your yard, you should be able to get the gold out of it, or the diamonds, really find something that's going to make you wealthy. And so you had a lot of really weird chemistry going on during the time. It wasn't until the late 1700s that you actually started having some chemists looking and saying, okay, let's go back to that whole atom thing over there. And the guy who first really started going back to the atom was a man by the name of John Dalton, and he came up with the atomic theory. Notice that there's a lovely little arrow beside his name. Write that name, John Dalton, down. Color that arrow in so that it actually pops up, and maybe color it a pretty pink color. Now, John Dalton had his opinions of what to call these things. He thought they were actually little indivisible spheres instead of what we think of them as today. But what we know today is that they're made up of electrons, protons, and neutrons. The electrons are negative, they orbit the nucleus. The protons are positive. They're found inside the nucleus, and the neutrons are neutral. They have no charge, and they're also found inside the nucleus. The electron is so light, it's almost massless, so we ignore the mass of the electron when we're talking about how heavy an atom is. Okay, so find on your notes, letter C, the atomic theory, states 5 things. 1, All matter is made of atoms. So you guys have known this since grade school. What is everything made of? It's made of atoms. Now, don't get this confused in your brain with cells. You know, we talk about what are all living things made of, and we say they're made of cells. But cells themselves, cells are made of atoms. All right? Number 2, atoms of the same element are chemically alike. Atoms of different elements are chemically different. That's a no-brainer. If you have a whole bunch of gold atoms, hey, what color are they going to be? Gold. You know, what are they going to feel like? What are they going to look like? What are they going to react like? They're going to react like gold. So atoms of the same element are like each other. They're chemically alike. And if you have a gold atom and an oxygen atom, are they going to be the same? No, they're going to be different, chemically different. Number 3, atoms of the same element have a definite average mass. That means if we get a whole bunch of gold atoms, we can look on the periodic table and find out what the average mass is, and that'll actually be what the mass is of the atom. So if you have 1 mole of atoms, of gold atoms, they'll weigh a certain amount. And when I say mole, a mole is the amount of stuff that has 6.022 times 10 to the 23rd pieces in it. And we use that number, we use that amount a lot in chemistry because, you know, it's not practical to say, well, we're going to pick up 1 gold atom. You know, they're too tiny for us to deal with like that. So when we talk about an amount of atoms, usually we talk about them in terms of moles. It's kind of like a dozen is 12. A mole is 6.022 times 10 to the 23rd. Now, I say they have atoms of the same element have a definite average mass. That means if, and I don't have a periodic table in front of me, so I'm not sure what the masses of the things are, but if we have oxygen atoms, then in general they have an average mass of 15.9999 grams for 1 mole. That's an average mass. It doesn't mean that you can pick up 1 oxygen atom and it will weigh 15.999 atomic mass units. It doesn't work like that at all. However, it does refer to the fact that it's an average mass. We have 2 numbers in each box on the periodic table. There are 2 numbers. One is the atomic number, which tells us the number of protons, and that's a nice round whole number. So you have 1, 2, 3, 4, 5, 6, 7, 8, and so on. And then you have the other number in there, and that's the mass number, the atomic mass number. And that number is not going to be a nice, perfect little rounded whole number. It's going to be like 15.999. And that's an average. And you guys all know about how to do averages. It's a little bit different when you're talking about the mass number, but you have the general idea of what to do. So the average mass of oxygen won't be the same as the average mass of gold. That also makes sense. You know that gold is much more dense than oxygen, right? Okay, number 4. Atoms of different elements have different masses. So again, if you've got the atoms of the same element, they're going to have the same average masses. If you get gold and oxygen, they're not going to have the same mass. Again, you know, don't overthink it. That just makes sense. And number 5, finally, atoms can't be split by ordinary chemical means. Now, we can do some freakish stuff with the whole big cyclotrons and the atom splitters and all sorts of weird stuff, but that's not normal, ordinary chemistry. You know, you can't dump an acid onto gold and all of a sudden you can pull out the protons and the electrons and the neutrons. It doesn't work like that. So atoms can't be split by normal chemistry. They can be split by nuclear chemistry or nuclear physics. But we're not doing that here in this class. We do ordinary, normal chemical